Some record. This is quiz. Okay, there are two questions. Just try to write it. Whatever you remember. Okay. Hydrodynamic boundary layer. That one is straight from fluid mechanics. We took fluid mechanics, you know already, right? Last class. With the broken boys, I was trying to explain. Remember the boundary layer? That's the thing that I was talking. Then the thermal boundary layer thickness. Remember, these are analogous of hydrodynamic boundary layer, but it could be matching, it could be low, it could be high, depending on the fluid that is going on the top of it, right? So that's the thermal boundary layer and the Reynolds number. Okay, I'll check, start the quiz. Reynolds number, Nusselt number, Prandtl number. Here I was talking about the Nusselt number. So the Banach number, remember? You do know the Banach number, right, everyone? Alright, so the Prandtl number, I didn't talk about it that much, but if you watch the video lecture, both of them, you should be able to answer both of them. All of you watch the video lectures, right? Should be feeling well comfortable. Don't worry, I'm going to give you the understanding and say benefit. Please take 5 minutes, okay? I don't want to bother you next 5 minutes. Okay, you guys are done? Give me some more time. Okay, I'm seeing you guys are still ready. Some of you. Take 2 more minutes, I guess. Are done? Still you're done? David, you are done? Ale, you're done? I think you need more time. It's okay. I'm not grading anything, okay? So just let's focus on these things. Most of them are done. So hydrodynamic boundary layer. You guys remember from fluid mechanics class? If this is the plate, if fluid is flowing on the top of it, right, with the velocity u infinity, all right, and then you can say like this temperature is T infinity, okay, and then H is the convection coefficient, all those things I'm putting it here. Then there are two different kinds of layer happen. First one is the hydrodynamic boundary layer, okay, and the hydrodynamic boundary layer has a transition, right, where the Reynolds number equal Reynolds number critical. Anybody remember the value? 500,000, right? All right, so this segment here, if you remember for the hydrodynamic boundary layer, fluid flow is much more orderly fashion. They call this thing laminar or turbulent? Laminar. And here things are all about the places, right? Fluid flow, this is turbulent, okay? So first of all, the hydrodynamic boundary layer, if you're going to say this is my hydrodynamic boundary layer, sorry, say if you're going to say this is my hydrodynamic boundary layer, you can say this is delta, right? That's what they use for hydrodynamic boundary layer. Now the thermal boundary layer, okay, it is something very similar to hydrodynamic boundary layer, okay, but it may match with the hydrodynamic boundary layer, or it may be lower than the hydrodynamic boundary layer, it may be higher than the hydrodynamic boundary layer. How it get dictates by the Prandtl number, okay? You've watched the video lecture, right? I thought I explained that, right? So the Prandtl number dictates that. So what I'm trying to say here, you have this thermal boundary layer. It could be something like that, depending on the Prandtl number, or it could be something like that, right? Okay, it can be any place, depending on the Prandtl number, obviously. And the symbol they use for this is delta T. Okay, now the exact definition of both of them, like hydrodynamic and thermal boundary layer, is, you see, for hydrodynamic, assume that the velocity u infinity, okay, that is the free stream velocity. Everyone remember the free stream term from fluid mechanics class? Again, you remember the free stream velocity? What is free stream velocity? Free stream velocity is the velocity that is flowing freely, right? So if the velocity of the air that is flowing freely on the top of this, right, what will happen here? Because of this boundary layer, what is happening here? I think you got to pay attention. Because of this boundary layer, what happened here? You see, this free stream has an effect, right? I would have to see what I'm showing, right? The free stream does have the effect, right? Free stream is coming on the top of it because of this boundary layer, right? It does have an effect. Because of that, right? The free stream velocity changes. Free stream velocity changes, right? From this point to up to this layer, that line that I'm drawing, the velocity is different. So the definition of the boundary layer is, you see, when the velocity is say or 99% of the free velocity. Does it make sense? When the velocity is almost same, that 99% of the free stream velocity inside the boundary layer, that's where the transition happens on the boundary layer. Now, do you see the boundary layer physically? It's not been seen, right? So like you gotta find the boundary layer thickness. You know, thickness means the delta value. You understand the thickness, right, Hamid? You know the thickness, the delta value. To find the thickness, you gotta use that equation that I just mentioned. The free velocity should be 99% of the velocity that is impacted due to the boundary layer. The same thing is true for the thermal boundary layer. The temperature T infinity that you are seeing and the TS is different, right? That's why the temperature exchange happened. That is 99% at the boundary layer. Does it make sense? You understand? So that's the definition. I quite didn't put this thing as like, so this is the temperature TS. So now this TS could be, the TS could be higher or lower than the T infinity. It could be anything, right? Depending on that, whether the TS is higher or lower, the plate would be absorbing heat or releasing heat. Does it make sense? It could be anything, right? It could be like this or it could be like this. Doesn't matter. So Reynolds number. Everybody remember Reynolds number definition? What is Reynolds number? Yep. Let me give you the rho Vd by mu or rho Vl by mu, right? Let me give you the definition in terms of parameters, right? Then I'll talk more about this, right? It's an inertia force. It's a ratio of inertia force and the viscous force. Make sense? So that's what the Reynolds number is. Inertia force, anytime you see inertia, that means the velocity. The velocity is there on the numerator. Okay. You're seeing the mu, mu is the viscosity. The viscosity you're seeing in the denominator. So that's why it's saying like it's a ratio of inertia force versus viscous force. Okay, that's what the Reynolds number is. Okay. Now this L and D, those two different things I use for the same Reynolds number. Okay. And you might be wondering when to use L, when to use D. You may know it, right? When to use L? For flat plate, right? And external flow. When to use D? The internal flow pipe, right? The pipe flow. Makes sense? So the same question, like same thing can be written in two different ways, depending on the situation. So if you are dealing with say like external flow, this is so important, so I'd like to emphasize it in a descriptive manner. Say like this is your L, right? And because of the flow you have this pattern, right? What I just did here before, and this U infinity, T infinity, right? H, all this cloud is representing that, right? Okay, Isaac, you gotta be really comfortable what I'm doing now. You gotta be, in order to understand this convection, there's no way around. Okay, there's no way around. You gotta be really comfortable, focus on what I'm saying. Okay, you may feel like, okay, I'm giving the homework, you're gonna get solution manual somewhere, submit it, and take home exam I'm giving, so you are getting solution somewhere. That way, what you are achieving here? Nothing. You're not learning anything, right? I've been doing this more than 15 years. By seeing the face, I know who is understanding, who is not understanding, who is listening, who is what doing what, right? So please respect my time, your time at the same time. Try to understand your best. Does it make sense? This is very important subject. If you're a mechanical engineer, if you don't know the heat transfer, it's not too good. It's not too good for you at all, because heat transfer is one of the main branches. Okay, just like design, heat transfer is one of the main branches. Okay, fluid mechanics. These are the main branches. You really need to know this stuff. Okay, you never know when to use them. If you carry a certificate mechanical engineer, BTech mechanical engineer, that means everybody is gonna have an assumption you know heat transfer, you know thermodynamics. That's the main branch. Fluid mechanics, heat transfer, fluid mechanics, thermodynamics all goes together. Okay, all right. Sorry, I mean I could have not saying any of this, but I just want you to do good. Okay, just for your own sake. Please try to put your attention 100%. So anyway, so U infinity, T infinity, and H. You understand that those things always you want to put it over there. And then this boundary layer thickness that I was saying, you see, I don't want to repeat the same thing. Just quickly, I'm writing it. Say like this is the hydrodynamic boundary layer, right? This L, this is the flat plate. You understand that? How do you understand? This is the flat plate. So when you're dealing with the flat plate, this L or X, right? Those are important. So Reynolds number goes with this term, okay? When you are dealing with, say like internal flow. Excuse me. That's the diameter, right? And now you're dealing with this. Make sense? All right, perfect. So this Reynolds number done. Any question? You remember that? Isaac, you remember? It's a inertia forces versus the viscous forces. What does it tell you? If you have a high Reynolds number, that means obviously the inertia forces overdo the viscous forces. Does it make sense? Okay. Means the velocity is really high. Means the flow is really high speed flow that is flowing on the top of it. Okay, then the Nusselt number. Okay, Nusselt number. David, did I explain those Nusselt number, Prandtl number in the second lecture? You watched the second lecture, right? Did I explain those over there? You know, Logan, did I explain those? I didn't explain the Prandtl. Okay, no. All right, let me explain. Okay, so the Nusselt number. So let's talk about the Nusselt number. So the Nusselt number is remember HL divided by K. That's the same as the Biot number. Okay, this is the same as the Biot number. So this L here, what is this L? What do you think, Isaac? The L should be same as like the Reynolds number L, right? Make sense? Okay, so now I'm gonna say write the Nusselt number for internal flow. Can you do that? What you'll be doing instead of the L, you'll be putting what? The diameter. Make sense? Do you understand? So that's what the Nusselt number is. Now, while you are dealing with that, remember that our ultimate goal is to find the value of the H, so we can find the heat transfer, right? So to find the value of the H, if you can somehow find the relationship of Nusselt number, Reynolds number, and Prandtl number, and able to solve the value of the Nusselt number, and from there you are able to solve the value of the H, then you're golden. You can find the value of the Q. You remember what is the Q equation? I said H A del T. So if you find the H, that's what you need for, right? Does everybody check that I uploaded the equation number in the bright space? If you haven't, it's all right because last day was not a good day for me. In terms of the vocal issue. Please see the bright space question number. I'm gonna talk about it in the class. Plus, take a look on that. Okay. Why did I upload? Why upload? Everything is important over there. Okay. Any question with the Nusselt number? Everyone understand it? Kind of, I guess. So this can be also written as what? H D over K. You understand that? And then you can say, you oftentimes you'll be seeing they put a D as a subscript and they put a L as a subscript. Now, the other very important thing that I would like to cover is H. Whenever you don't have a bar on the top, that means it's local. How do you remember what is the local H and what is the average H? What is the difference? Last class, and my vocal was so. Anybody remember what is the local H? What is the local H? At the point of interest, right? Say like, everybody please watch what I'm trying to show. Say like the H value I'm trying to find, right? On the top of this plate, right? So at any point, the H value will be different. Does it make sense? You understand that? Because at any point, the boundary layer, right? The boundary layer is different thickness, right? If the boundary layer is different thickness, that means the H value will be different. The boundary layer means what boundary layer? Is it the thermal or the hydrodynamic? Which one? It's always been thermal, right? It has something to do with the thermal. If there is no temperature change between the plate and the gas that is flowing on the top, there is no heat transfer. There is no H. You understand that, right? But if there is a change of temperature, then the thermal boundary level will change. And why it is changing? I said, because of the boundary level, it is changing. So every point, the H value is changing. You understand that? Do you understand this? Okay. So now that you understand, so at every point H is different. That's called local H. And that goes with this Nusselt number. You see the H that I have over there doesn't have a bar on the top. Now, what if you are interested to find how much of the total heat transfer happened? Okay, I said, how much of the total heat transfer happened on the top of this plate? Then, can you able to find it like at every point H value and then kind of find it and add it? Doesn't make sense, no average. So you need to find the average H. Average H the way to put it like H bar. They put a bar on the top. So in my lecture, I did cover that, right? Those video lectures, everybody watch those, right? I did cover the averages, remember? So that's called averages. Now I'm gonna write it here. Okay, by the way, the agenda, after this quiz thing that I'm doing, the agenda is I have what is for math problem. I'm gonna do it with you guys. And I have another one which you have seen in the video. Okay, I'll explain that. It makes sense? So I would like to make sure everybody understands it. How many math problem I solved in the video? Is it one or two? I believe one. Just one, right? So the math problem that you've seen, I solved it in video. I'm gonna go through that, okay? And I have one math problem which we're all gonna go together, okay? And then you should be feeling comfortable with the homework. So that's the plan. Okay, come back here. So these are local. So they call this thing. Everybody wanna write this thing. They call local Nusselt number. Okay, and then you can say like average Nusselt number. So when I'm saying average Nusselt number, you definitely want to write what I'm doing now, because in the equation manual you'll be seeing using this all the time. Then you're gonna feel confused. What is happening? This is what happening. Okay, so write it so you're gonna remember. So the average Nusselt number is, and you want to put a bar on the top, H bar L K, and this can be also written NUT bar on the top, then K. Everybody understand this? You definitely want to write it. I'm not saying everybody's writing. Okay, so the other thing that I want to write it here, this H here is local HT. What is HT means? Heat transfer, right? Coefficient. H bar is average heat transfer coefficient. Okay. The final thing left here is the Prandtl number. I didn't talk about it. I'll talk about it now. The Prandtl number, definition of that. If I don't learn more about it, I just want to discuss it. So you'll be dealing with this kind of thing. Please check. Please check. I'll show this equations shortly after this. So there is this Prandtl number is a material property. Okay. So then the Prandtl number. So Prandtl number PR can be used mu by alpha. Yes, mu Cp by K is the ratio of momentum diffusivity to the thermal diffusivity. So they call momentum okay, so this thing can be written as nu here. It's called kinematic viscosity. Okay, so this nu can be written as mu over rho. Excuse me. Then thermal diffusivity, which is alpha K by rho Cp, where this mu is dynamic viscosity. You know that, right? And Cp is, what is Cp, Matt? Heat at constant pressure. All right. What is K, Isaac? Conductivity, right? They call thermal conductivity as well. So the Prandtl number, very important. Just remember this way. It relates the thermal and velocity boundary layer. Anytime you see me writing BL means boundary layer. So it dictates whether the momentum or heat transfer, which flows faster. You know, momentum means like the hydrodynamic boundary layer, right? So this is very important. Whatever I just wrote over here, and you'll be seeing it in the equation, all the time. So you really need to know the fundamentals of the Prandtl number. Okay. First of all, if you would like to say anything about the Prandtl number, you'd like to start with this way. Prandtl number is a dimensionless number, right? As like the Russell number, as like the Reynolds number. Okay. Secondly, what Prandtl numbers do? Prandtl number tells you the hydrodynamic and thermal boundary layer relationship. In other words, whether the thermal boundary layer is higher than the hydrodynamic one, or is lower than the hydrodynamic one, or it's same as the hydrodynamic one. If I'm going to ask you a question, a common sense question, if the Prandtl number value is 1, if the hydrodynamic boundary layer is higher than the thermal boundary layer or lower than the thermal boundary layer, or is the same? It's the same, right? So I would have like skipped the same thing that you made. You understand what I'm trying to say, right? Everybody understand? So it's so important. So like you got it. There is a homework question. Anybody started the homework? There is a homework question that asks you to use the Prandtl number value and find the thermal boundary layer thickness. Okay. Now that question does have the hydrodynamic boundary layer thickness as well, right? So there is a equation that I'd like to share with you now, which can be used to find the hydrodynamic boundary layer. And there's a relationship with the Prandtl number and hydrodynamic and thermal boundary layer. Okay, so I will show you that one as well. And those are in equation. Next thing I'll be doing after you've done with understanding everything, I have a little bit more to talk about it here with the Prandtl number. Then I'm gonna show you the equation number. Everybody's with me so far? Understand? I think you understand everything. You're also sick like me. I know. Are you catching the cold? A little bit. Yeah, I've been like last 2 nights is horrible. Anyway, so if anybody feels sick, like don't push too much, okay? Just try to be with us, whatever I'm doing. Okay, so the Prandtl number, you understand about that, right? The relationship of hydrodynamic and thermal boundary layer, as I said, right? Or everything that I explained. Now, the other important thing, the parameters, all these things that I wrote over there, right? Very important parameters. Okay, let's try to understand one by one. So, is the ratio of kinematic viscosity? Okay, see that kinematic viscosity mu. Anybody have seen this? How do you remember the mu that you use in fluid mechanics class? You didn't. When I was in fluid mechanics class, I knew that. So mu is mu over rho. So the mu is also called viscosity. Right? They call it kinematic viscosity. Okay, and mu they call it dynamic viscosity. Okay, and those two are related by rho. Or rho is what? I said density, right? We use rho for density usually. So rho is here in this is density. Okay, You understand so far? That's the kinematic viscosity. Okay. Okay. Now you know the Prandtl number is a ratio of that viscosity kinematic by thermal. You're seeing it over there, right? Thermal diffusivity. What thermal diffusivity means? It divides by this equation K over rho Cp. What does it tell you? This K tells you how fast the heat is going to flow. Remember that conductivity? Okay? So K over rho Cp is the capacity of the heat, how much it has. Right? Okay? And rho is the density. Now you understand all the terms here, the Prandtl number, everything that you're seeing. Everybody's feeling a little bit confident? Any question with the Prandtl number? Remember, if anybody asks you what is Prandtl, two things you say right away. First, it's a dimensionless number, okay? And second, it relates the thermal and the hydrodynamic boundary layer. It tells you how big of the thermal boundary layer compared to the hydrodynamic boundary. You now know the boundary layer, right? I was trying to explain it last 30 minutes or so. What are those? Is it right? Feeling confident now? A little bit? Everything's good? Feel confident? Okay, now I'm going to show you some equations. And then you're going to feel more excited because if you understand this equation, you can use this to solve the math problem. Okay, let's do that. And you see what I'm doing, I'm getting it from the bright space. So you know where it is located. You have the access of it, okay? Do you see I create a folder called equation manual? Everybody see that, right? All right, so you want to open this convection. Okay, this is where I'd like to pay my attention. Okay, these two equation. So these two equation is so important. For some reason I'm not able to. Do you see these two equation? I want everybody to write these two equation. Okay, no exception. Everybody write these two equation. Okay, and you can see the first equation is telling you how to find that. How to find that? Delta. They call it delta. Okay, how to find that delta. Okay, delta, and that is the hydrodynamic starting up. The first equation is the hydrodynamic boundary layer, right? So you see here, it's very straightforward, right? To find the delta at any point, right? You remember that goes for laminar and then goes for tubular. If you're trying to find at any point on this plate the delta value, you have to know what is the x value at any point, right? From this side of the plate, so like this is 1 meter, 2 meter, 3 meter, 5 meter, right? Based on this x value, you should be able to find the delta, okay? How big it is. Once you have the delta, then use this the next equation to find the delta t by using the Prandtl number value, okay? Very important question, and you should be able to solve one problem, homework number one problem without any issue by using these two questions, okay? The right way you should be able to solve. And the first equation, you know where it came from? Did it came from heat transfer? No. It came from which class? Fluid mechanics. Did you guys learn it in fluid mechanics? You might, probably. You might forgot now at this point maybe. And this is what you learn it from fluid mechanics, the first one. The second one is addition, there is heat transfer class. Where you know what is the thermal boundary layer now, and you know the relationship of the hydrodynamic and the thermal boundary layer, which triggers by the Prandtl number. And remember, I was saying about the Prandtl number. Prandtl number is a property of the material, right? It's a property of the material, okay? So for as an example, for air, it has a one value, which is kind of fixed because it depends on the temperature, but kind of like in a regular temperature is kind of one value. So for air it's one value, okay, Prandtl number I'm talking, right? For water it's different value. For engine oil it's completely different value. For another refrigerant it's completely different value. So you will be applying this, okay, in different practical application. You are using the Prandtl number from appendix. You know what is appendix, right? In the appendix, they have the Prandtl number for everything. Okay? Whatever needed. So in the math problem, whenever you're trying to solve and you find the Prandtl number, don't get frustrated. Just go to the appendix. You'll be able to find it. Now you'll be seeing probably for temperature the value is different, but you will probably getting the approximate value for the temperature that you are dealing with, right? Huh? That's not a V, that's mu. That's a Greek letter, okay? Yeah, that's people usually use it for thermal viscosity, okay? And the V value, you would be finding either there's two different books. One book, like Sandial or Copenhagen, has the mu value directly given. In other book, they don't have the mu value directly given. They give the mu and the rho separately, the dynamic viscosity and the density separately. So once you know that, right, you can able to find the value of the mu. Okay. Something very important just happened, like these two equations, you need it for question number one. I believe everything is in record because even though I'm here, I don't know how much of recording happened in terms of the sound. But as a please review. If you didn't understand, please come talk with me, okay? Next week, I'll help you in person. All right. I mean, see, I have like around 10 students. How many is this? So therefore is missing the family emergency right? This Chelsea didn't show up, Mitch didn't show up. Those who didn't show up, I feel like okay, whatever reason, it's beyond my control, right? Those who are here, you are taking the time, right? You are interested in water. So when you are coming here, my goal is to give my best, and your goal should be take the best. Does it make sense? Try your best to get the max out of it. Because this is important time that you're spending here, okay? And it's an important topic that you're trying to learn as well. All right, moving on. The other thing is this equation. Remember, I was talking about this H bar, total heat transfer rate Q, and the average convection coefficient H bar. Remember, I was talking about that. So these are here, these equations, okay? Now I'm gonna actually go to our actual thing, means the problem itself, okay? And before I go that, I'm gonna explain you this problem that you have learned it in. This problem you have learned it in the video lecture, right? Everybody watch this problem in the video lecture, right? Matthew, watch the video lecture. You're gonna need to follow up. Please do that as you can. Guys, if you watch the video lecture, both of them, you must have seen me solve this. Did you understand? When I was fully understand? I was able to follow along. Okay, perfect. So it's the time for you to ask me questions if you have any, right, on this problem. Steve, Logan, you guys understand fully this problem?
I didn't understand the first two C1 and the C curve that's given there.
Oh, why they have these two different values? By the way, this is a very, very important problem. Why? We'll be saying something similar in next time. And the homework. So the second problem in the homework is this. Something very similar to that. Okay? Alright, so let's start with the first question that I have from Logan. Logan is saying like he didn't understand that two C values that is given here, right? So these two C values, by the way, those two values are constant, okay? And the H values are given for laminar and turbulent. Those are referring to the local heat transfer coefficient. Now, when it says here H laminar and H turbulent, it's referring to. That you remember, like the boundary layer is like this, right? So obviously, because of the boundary layer is different, the H value is different at different places, right? So that's the local. So now, when you're talking about still like the laminar section, which is up to this, and the turbulent is different, forget about it. So the laminar itself, right? So if you are given an equation which can be used to find any H value at any point, that's what it is, the first equation. As you can see, how do you know? Because it does have a constant C, C is a constant value, and it has an X value. And you know that X is equal to value, right? The X is equal to value, right? From here is X is 0, here X is 1, 2, 3, that way, whatever unit you have, right? It makes sense? So you see, there's the first equation for up to this section. And the second equation they gave you, remember, the boundary layer goes like this, and then this, right? For turbulent section, they're saying use that one, H turbulent, where the C is constant and C turbulent, and then the X value, whatever the X value here in this section, right? So it could be like 4, 5, 6, whatever X value for the turbulent section. Just plug it here, find the lower H value. Makes sense now? So you understand now?
So you use those two to get the
For local H. Yeah. So these two equations are representing finding the local H at these two different sections. Now what's our goal here? Overall goal. Our overall goal is to find the total heat transfer for the whole plate, right? That should be the goal, right? Usually, now they just give you the local H equation. Now, tedious way could be your mind should come up with, okay, I should be finding for every X value the H value and then find the average and then use the Q equation. That's tedious, right? You don't want to go that way. So easiest way is always do the integration. Okay? Right, Isaac? You're gonna do the integration. What happened then? You're gonna do the integration, you should be able to find for this whole section the average H. Once you have that average H, then use that to find the Q value. Okay? Any questions so far? Alright. Any other questions that you have when you are watching the video lecture? Any individual question you have? Any other question when you watch? Don't worry, I'm gonna go through that in 5 minutes or so, right? Just overview kind of the whole thing, right? If you don't have any personal question, then I'd like to move on. So, do you have any questions? Please?
So you wouldn't use those two for that.
You're gonna use those two for the average, and these are local H. Okay, so you're gonna do the integration to find the average. The integration for the whole plate length. Make sense? Because the X is the length direction, X direction. Okay, so let me go through the problem more. First of all, lots of given here. Okay, so you see the water flows at a velocity u infinity is given as 1 meter per second, right? The plate length is 0.6 meter. Consider the water temperature approximately 300 Kelvin. Oh, by the way, you have noticed that air is not flowing on the top. Here, water is flowing on the top of the plate, right? Okay. Anything come up in your mind like practical application? Water kettle, right? Any time you have water flowing on the top of the surface, which the surface temperature is different than the water temperature, this is the scenario. Think this way. Make sense? All right, now moving on. So they said like the water temperature is 300 Kelvin. The laminar turbulent region, they have this local H, I did explain them, and the C values, I did explain them. Okay, so they are asking to find the average H. And again, in homework you would be doing, in exam you would be seeing a similar question. So very important one. Okay. All right, so average H for the entire plate. All right, so I have all the givens here. And that's the thing that I'd like to highlight. You always like to write U infinity, T infinity. Those are for the velocity and the temperature at free stream. Infinity means free stream. You'd like to use those symbols. Free stream means why they use the infinity? There's a reason behind that, right? Think this way. So you see that comes like this, and everyone else says an infinity. But an infinite amount of place, as if like the free stream velocity is the same. Infinite amount of the place, as if like the temperature of the free stream is the same. You also getting cold? Yeah. Also, this season is so bad. I can't sleep at night. I wanted to cancel the class again today, but I'm feeling much better in vocal cord wise, like last time. All right, so you understand that infinity. So U infinity, T infinity. What is the length? They said like 0.6, right? They have these two local H equations, right? They have these two constant on those two equations, right? They are asking to find the average H. You understand so far? Okay, I'm assuming, I'm an impression, because this was solved in the video lecture. I'm an impression everybody watched that video lecture, week 10 lecture 2 uploaded over there, right? So that would be the lecture that I'm doing now, week 10 lecture 2 part 2. That way you can think this way, right? So everybody should have it already. Okay, so then there are some assumptions, and again those things are also solved and uploaded in Brightspace. Okay, for your reference. Just want to give you a heads up because you don't have the access of this anymore, the OneNote. So I put it over there. So you have the density of the water, absolute viscosity of the water. Why do you think you need those two values, density and absolute viscosity? Anybody, any idea? To find the Reynolds number, right? You remember the Reynolds number equation, which is what? Rho b d by mu, right? So these two, you always find it from appendix. These are properties, right? Mu or viscosity and rho. And there's V. This B, don't get confused with the symbol, okay? Isaac, it could be U infinity or the V. The same velocity, okay? You understand? The V is usually used for velocity, but if you see like, okay, I have it defined it U infinity, what does it make sense to find the Reynolds number using the U infinity instead of the V? Doesn't matter. It's the same thing, okay? It's the velocity. So you know this. Do you know the value of the L, the length of the plate? Yeah, I definitely know this. So can you find the Reynolds number? You definitely can able to find the Reynolds number. So why do I need to find the Reynolds number? They are so important. I did explain it, right, in the video lecture, those who watch it. So once you have the Reynolds number, then you can compare the Reynolds number versus Reynolds number critical. Matt, you remember what is the Reynolds number critical for the flat plate external surface? Is 5 into 10 to the power 5, right? That's the critical. What the critical is for? Local critical is for the transition where the laminar to turbulent happen. See what I'm doing here. I'm finding the value of the XC. What is XC? XC is the position where the transition happens. Okay, I think what is happening here? See, laminar turbulent. If X value is 0 here, at this point it is XC. You understand how it? If the whole plate is 0.6 meter, so like at 0.43 meter, like somewhere around here, right? The transition happens. Make sense? So to find the value of the XC, I need the value of the REXC, or the Reynolds number critical, which is 5. And by the way, in your homework, you'll be finding XC value as well. Okay? There are 4 problems in the homework, right? So in the first problem, I said easy peasy, 2 equations you're going to use, right? You don't really need anything else. It's just 2 equations you're going to use. First problem. You can keep by yourself. The second one is similar problem that we're seeing here, right? So to solve that second homework problem, you can do it by yourself. Okay? You don't need anybody's help. Understand? As long as you have like little bit gaps on that integration. Make little bit gaps on the integration, you need to know the integration knowledge. Okay? Alright. Everyone understand about taxi? Are you feeling good? Isaac, do you have any question with taxi? Think this way, Isaac. Say like the whole plate is 0.6 meter, right? So x is 0 here, and x is 0.6 here. At x is 0.43, the transition happens. So it's like this and then this. Okay? Got it? Okay, perfect. All right, so laminar and turbulent. So this is the integration that you really need to understand. And just try to make it a little bigger. I have a big math problem to solve. I don't want to do something hastily. I think I've given you enough theory today, right? So I don't really want to do something hastily and kind of undone way so you don't understand it fully. So rather you want to understand it fully, right? Because I was not there watching the I don't know how much you understand. It's like COVID period. The thing happened during the COVID. Only I don't know, maybe 10-20% students was able to understand the whole thing. Rest of them were not attending at all. I don't see them. They didn't open the video lecture and so they didn't open the video cam. They were probably wondering what this is. I don't know. But I know kind of by talking with them, like they were not understanding. In this class, I have a good feeling like almost everybody is understanding, like because I can see your face, I can interact with you. You can ask me a question, right? In person is really good. So all the thing I said, like because you have to watch the video lecture with Ken lecture too. I don't know how much you understand, right? So this is your opportunity to interact with me, make sure you understand the whole thing completely. Okay. Again, come back to the point. Okay. So what's our goal? Our goal is to find the H or the average H. And I did talk about it. Why? To find the Q, which is average H from the reality. Now, after finding the average H, we're going to do the integration because I integration do? Do you know that? Integration deals with the infinitesimal distance. You know infinitesimal distance? It's like very, very little. I mean, that little is like a atom. It makes sense? So if you have an equation, this is continuous equation, and you do the integration, you should be able to find the average age. Okay? As you understand, average age for the whole plate. Okay? So here's the issue. Now, I know my XC value is less than the total length of the plate. That means I have both types of layer, laminar and diagonal. Okay? And I was given with both equations for local age, right? Laminar and turbulent. So I'm gonna do what? I'm gonna do the integration for the laminar section and the turbulent section, right? As you understand? Okay. Now here's the thing. For laminar section, the age equation that is given for local age. I'm going to use that in integration anyway. But the limit, you guys remember integration limit, upper limit, lower limit? The limit should be what? Limit is the x value on top. The limit should be 0x when the x value starts from 0 to what? 0.43 or xc, either way, right? Everyone understand this? Everyone understand? And that's the thing we're seeing here, right? 0 to xc. Are you seeing that? Everybody, pay attention. Are you seeing it here? 0 to xc. The limit. And did I write the laminar equation here? I did, right? I did write the laminar equation. Everybody agree? Agreed, right? Okay. For turbulent, do I need to use the lower limit of x0? No. Because, think about it. Turbulent happened, it's a laminar up to this, and turbulent happened up only in this section, right? And this section begins, what is the xc value? 0.43. That should be a lower limit, right? Xc. And what is the upper limit? The end of the plate, like L. Now, everybody understand this equation? Everybody understand this equation now? You understand? If you understand this, rest is math. The math can be understood by any math tutor, okay, from the math previous background, okay? But I can also, with understanding, I probably explained the math as well, right, in the video. So if you understand up to this, what I just said, and if you understand why I'm dividing this by 1 over L, because when I'm doing the integration, h multiplied this dx, this kind of L thing came up over there. So L needs to be cancelled out, because our ultimate goal is to find h bar. If you understand this is fundamental, rest is math, means I'm just doing the integration, and I'm plugging on the values, and I'm finding the value of the h bar. Is it me so far? The rest portion, I feel like you can able to resolve it. If you can, let me know, I'm going to help you in person how the integration is done, okay? If you couldn't catch it, get a hold of me, just get a hold of anybody. Anybody can explain you the integration, any instructor, any MATLAB, any tutor in the library, anybody can. It's the easiest integration ever. It's the fundamental integration, okay? If you have issues, you could have, I'm not saying it's bad thing to have, if you could have issues understanding integration, just come talk with me. If you find me, just go to the library, talk with any math tutor. They're going to give you the understanding anyway. It's so easy. But they will not going to give you the understanding of any of the things that I was saying before. What is h bar? How we are dealing with, like, 0 to xc. They don't have any clue of that. Maybe if they are not mechanical engineers, maybe they teach us a before. Make sense? Alright, that is important. In this class, you should be able to understand why I'm dealing with the integration 0 to xc, xc to L, right? Why I'm using what equation, the laminar and turbulent in two different integrations, right? Why I'm doing this integration. These are the things you should be questioning yourself, and you should be understanding it properly, okay? Understand the integration properly. You understand? Alright. Moving on. I do have some time. I know it's a long class, okay, but still, let's try our best to deal with another math. And that one is this one I'm talking. I have like around 14 minutes left. That is enough, probably, to just give you the intro and at least do something about it. I feel much better today because I was able to give you some understanding. Like, in last class, I was not able to give you that much. And I was feeling bad, like you are falling behind. And there is another problem that is happening in second week of April. In second week of April, I'm going to North Carolina. I can only do, I'll be missing both classes. So 14th to 16th, I will be in North Carolina for AWEX symposium. There's a masking I gotta go over there related to the school, nothing personal. And the only way around could be, unfortunately, that's the only way around. I do have the video lectures, right? So I'm gonna upload the video lectures. You're gonna just watch these video lectures. I'm gonna possibly give you some tasks, do the homework and everything. Okay. But what I may do, like, during the regular time when I'm coming to Hardwick, just you talk with me during the office hour, or just try to get the full understanding. Okay, whatever happened. I'll also try to explain the way that I'm doing now the video lectures, what I'm doing. Okay, but still, there are two, but 1 week is two full class. So many things I'm gonna cover. Okay, on this video lecture. So I can rely on you. You're gonna watch it, right? Watch it minutely, take notes and everything. Because I'm leaving on Tuesday. My flight is around, like, it's from Montreal, so there's no I can do the class here. So around 12ish my flight, so I gotta go early morning over there in Montreal. Okay, because I want direct flights. I gotta go Montreal, and then from there I'm gonna go. All right, so that's that. Just 1 second. Okay, read through the problem. Everybody, please read through the problem, and start with the givens. All right, so let's read to the problem. Okay, first of all, let me give you the intro of the problem. Why you are doing the problem? By the way, there is a homework problem similar to that, and the same one from the last homework problem. Okay, the problem number 4. So what you're seeing here, you're seeing two turbines, right? Everybody know why do you have a big wind turbine here? What is the sorry? I said wind turbine. Why do we have a wind tunnel here? You guys know what is the application of the wind tunnel? In any universities you go, they have a wind tunnel, and they use it for research purpose and for class purpose as well. Anybody know what is the purpose of the wind tunnel? What do they do with the wind tunnel? Huh?
Aerodynamics.
They explore the aerodynamics, the fluid mechanics in wind tunnel, right? You at least have the basic idea, right? But application wise, do you know what is the application of wind tunnel?
You test like airfoils or downforce.
Exactly. Why do they test airfoil here? Because they need to scale it down to smallest, right? So what happened in the large scale, like in the airplane, the airfoil that they have, the airplane, the blades are airfoil shaped. You know that, right? And the engine. Okay. So in big airfoil, those are really big, right? Have you ever noticed how big those are? I mean, you notice, right? It's really big blades, right? So in wind tunnel, I mean, they are large scale wind tunnel in a big lab. They actually have that big tunnel to test it real time. But usually in a small scale in universities like ours and any other universities you go all around, you'll be seeing a wind tunnel which is not that big, right? So what they do, they scale it down by doing the dimensionless analysis method. Okay, so they scale it down the wind tunnel and they test it inside this wind tunnel, and they are representing or as if like they're mimicking what happened in the actual engine. You understand? Okay, so that's the reason you're seeing two different airfoil shape, two different airfoil, and one is small, another is big. Okay, so you are testing it in a wind tunnel. Okay, and you have this one is representing what happened with the other big one. Okay, so what they give you and what they're asking you to find. Let's go there. Okay, so they're saying in experiment, first of all, this kind of thing always happens in experiment. Okay, the temperature and velocities and the rate of heat, rate of heat from the turbine blade and the characteristics, the surface temperature and the Q1 all is given for the first blade. Okay, so in experiment they were saying what they were saying. Harley, focus on this problem. This is a new problem. They were saying, you see, the first blade. They were saying these two parameters. So they're saying like Okay, this L at the characteristics length is 0.15, right? For the first plate. They're saying, okay, the temperature for the surface is 300 degrees Celsius. They are saying the heat transfer that happened from the top of the surface is 1500 watt. Okay, and they're saying like the yard that is flowing on the top of this airfoil shape has these values like that. Yeah, temperature 35 degrees Celsius and the velocity is 100 meters per second. Right? Can anybody tell me why the airfoil shape turbine plate has anything to do with heat transfer? It has everything to do with the heat transfer. Why? When it is upon the yard, the temperature is way different than what is happening on the engine, right? The air temperature, you know that, right? The pressure and temperature, anybody notice at 30,000 feet, how much of the pressure and temperature? Do you guys ever notice outside temperature when you are flying the plane? No? It's a very low pressure and very low temperature. You know that, right? And you know the reason, right? The fundamental reason. So we are in the ground surface, right? Where we have the highest pressure, not highest, we're gonna go deep through, we're gonna have even more pressure. But at the sea level, we are on ground level, we have the highest pressure compared to anything above. Okay? You know that. So you know the reason I said why you have the highest pressure here? I'll come to the temperature shortly. You know the reason why you have the highest pressure here in the ground level compared to the anything up? Huh? Huh? It's the lowest, yes, it's the lowest point, but think this way, at this lowest point, what happened? You have the, as if like, think this way. So if you have a means, Ali, to get a cylinder like in my shape, right, and extend the cylinder from this point to the space, and if you have a means, okay, man, to somehow measure the weight of this area from here to the space, that here, the cylinder here that I'm saying, right? So it would be huge, right? Even though you feel like, okay, yeah, doesn't have any weight, and it does have a weight. When you're talking here to space. Does it make sense? So that's the reason you have the highest pressure because of the weight of the air layer, highest pressure here. Now if you're gonna go 10,000 feet up, you're not gonna feel that much pressure on the top of you. You'll feel all sorts of different things because your body pressure is higher, atmospheric pressure is less, right? In a cliff mountain, right? In Everest or wherever, you'll feel all different dynamics, right? You'll probably feel suffocated. All sorts of things may happen depending on your health condition, right? Your body will adjust, but it will need some time because the pressure is less. Because you know, if you're gonna go 1,000 feet up, or 2,000, 3,000 feet up, right, or 10,000 feet up, that much air layer is missing. From that point to the space, that much of air is missing. That's for the air pressure. And the same thing goes with the air temperatures as well. Make sense? The more you go up, the atmosphere and everything is absorbing the sunlight. So they are always radiating here. So when you're gonna go up, even though the energy is coming from the sun directly, but it gets heat up on the planet and different things. That's why these are constantly radiating, right? These are solid surface absorbing more heat. Does it make sense? So when you're going up, even though the sunlight is, even though the sun is nearest to that point, but still there's not that much going on over here to absorb that heat. So that's why you have much less temperature. You understand this? Why have much less temperature? And I'm saying like the turbine has everything to do with the heat transfer. Because you are most extreme temperature and pressure, right? Make sense? When it is flying, that's why this kind of experiment is so important. Okay, now come back to the original problem. Now we have a small plane and a big plane. So they gave you a bunch of information for the small planes and the big planes, for example, right? So as I'm saying, like this L characteristics that's what given, okay, for both of them. One is like half of the other one. The Q1 value is given for one. They are saying like find the other Q1, right? And they're saying like you see this A1 and A2, that has the same similar shape, both of them. So you can kind of cancel it out. Those are dependent on this L values, okay? So you get, the ratio would be same A1 and A2, right? Make sense? We'll understand it more, A1 and A2 ratio later when we go to the problem, but for now just understand this way. The surface temperature is the same because are a little different, like 300 and 400 degrees Celsius. They are also saying you see the air temperature is same, but the velocities are different in these two different planes, right? One is half of the other one. So what they're asking you to find? They're asking you to find the heat transfer from the larger blade, so Q2. Okay. Now you know to find the Q2, to find the Q2 or Q1, what do you need? H, right? You need H, right? Okay, so you got to somehow have the H value of H. How? See, the Nusselt of Prandtl number and Nusselt number, those three are related together. So always remember, Nusselt number is equal to the function of Nusselt number and Prandtl number. Okay? So you'll be using that relationship to solve this problem. So for today, I'll say like, I'm done. We have 2 minutes left. Why don't you finish the givens element? The main problem we're going to solve it next. Okay? Let me finish the givens and other stuff. Okay? Where you don't need to do that much of thinking. So givens. So you have 2 blades, and when I'm saying blade, that means turbine blade, okay? So on the blade 1, you have this Q1 is given as 1500 watt. This L1 is given as 1.5, L2 is given as 0.3, TS1 is given as 300 degrees Celsius, TS2 is given as 400 degrees Celsius, and for ER they give you the T infinity is 35 degrees Celsius, T infinity 35 degrees Celsius, V1 is 100 meter per second, V2 is 50 meter per second. Okay, and these are the givens. I mean, what I explained already. Okay, you want to take the notes and assumptions. I'm not going to do any solution, by the way. So I'd like to keep it as it is, so we can start it from here. So steady state, constant properties. And this number 3 is so important, that is surface area is proportional to L. And that is given in the question. Surface area A is proportional to L. Okay. And the solution, as I said, I'm gonna solve it in next class. We're running out of time. Okay. And thank you for keeping up your attention for so long. This is a long class, always very challenging. And you did keep up the attention up until the end of the class, okay? And I did record the lecture. I'll upload it in Brightspace. In case if you don't understand anything, you always have the access of the video lecture. I'm gonna upload it right away, okay? And the homework I did upload it, right, everybody? Okay, so you should be able to start doing the homework, please. Okay, sir. Okay. And I'll see you again on next week. Next week I'll be here. The week after that I won't. Okay, Tuesday, Thursday. But don't worry, I'll have the video lectures. I'm gonna give you specific tasks and everything, so you gotta just follow up those things. Okay.